Okay.
All right. Okay, so today we'll talk about the Minkowski geometry, right? We'll talk about geometry of space-time. Geometry of space-time, right? So all of the effects of special theory of relativity can be seen as a consequence of the underlying geometry of what we call as the space-time, right? And this formulation is very enlightening. It gives a geometric meaning to all the effects that we were talking about: length contraction, time dilation, and all this. Okay. Right. So before going to geometry of space-time, let's first talk about the geometry that we are familiar with: geometry of space. Okay, let's first talk about geometry of space. All right. Okay, now for simplicity, we know that space, we talk about three dimensions: dx, dy, and dz. For simplicity, let's take 2 dimensions. All right, we can easily generalize it to 3 dimensions. Okay, I'll mention wherever that's applicable, but the generalization is very simple. So for simplicity, let's talk about the 2-dimensional space. All right. So let's talk about 2-dimensional space. All right. So for a 2-dimensional space, we can have x-axis and y-axis. Right, we can have x-axis and y-axis. Okay. All right. So we can simply call it a space. All right. So just that's a funny way of calling it. Since we have x-axis and y-axis, we can also call it as space. All right. All right. It's called space, but I call it space so that I'll later make a connection with space-time. All right. So this will call space in the sense that there are 2 directions, independent directions, x and y. All right. Okay. Now, what's the geometry of this flat surface? What's the geometry of this flat surface or the plane? All right. So we can talk about the geometry of this plane. So we can either find the geometry using some sort of measurements, or we can say that let's look at let's just study this geometry, right? ds square is equal to dx square plus dy square. Well, let's just examine this geometry. Okay, so you already know that this is how we measure distances, right, between these 2 points. If this is dx and this is dy, then this ds square is equal to dx square plus dy square. Right? This relation is called the geometry. Right? In this relation, we have got all the information about the geometry. Okay, it tells us about the relation between 2 different points in this particular space. All right, and we know that this is called the Pythagoras theorem. Okay, and in 3 dimensions, you can easily generalize. You just write dz square, etc. Right, but we'll talk about 2 dimensions. Okay, now without knowing anything, right, purely mathematically, okay, we said we already know this, but without knowing anything, purely mathematically, you could just study this geometry, right? Okay, let's check the consequences of this particular geometry. And we could say that, right? What's the geometry? What are the consequences or what are the properties of this particular geometry? Right? So when we define a geometry, we are actually telling you how to measure. We are giving a notion of the distance between 2 points. All right. If something is not clear, you please ask. Okay. All right. So we have got this distance. Okay. Now we can ask the following question. Since this is a geometric quantity, right? Since this is a geometric quantity, this is something physical. It's geometric quantity. Okay, for this particular geometry. So for example, if you have a meter stick or a pen in this plane, okay, the length of this would be a geometric quantity, and this has to be invariant. All right. So we can look for the transformation. What are the transformations? What are the transformations? Or what kind of coordinate transformations? Okay, what kind of coordinate transformations leave this invariant? Leave d square invariant. Okay, what kind of coordinate transformations leave this ds square invariant? You can ask this following question. Because this is a geometric quantity, there has to be some coordinate transformation that leaves this invariant. All right, because coordinates are not physical things. All right, it's our convenience. Coordinates are our choice. It's our convenience. So there should be some physical quantity that's invariant under some coordinate transformation. But we are going the other way. We are asking what are the transformations, all right, of x or this coordinates that leave this particular distance invariant. Okay, and that you can find simply by inspection, right? Simply by looking at it, and by inspection, you know that this particular transformation x prime is equal to x cos theta plus y sin theta. All right, Now, this geometry we are very familiar with. That's why I'm just explaining this particular geometry, Pythagoras theorem. Or this geometry is known as a Euclidean geometry. All right, I'm just explaining this Euclidean geometry. We already know this, but I'm arranging it in such a way that it facilitates our discussion of the geometry of space-time. Right? That's why I'm discussing this. Okay. So we have got, just by inspection, we know that x prime is equal to x cos theta plus y sin theta, and y prime is equal to minus x sin theta plus y cos theta. Right. This is a transformation of the coordinates that leave this invariant. Is this obvious? I think it's obvious. Right. Why do we take cos theta and sin theta? Why do we take cos theta and sin theta? Because here you have got x square plus y square. Right, x square plus y square. So here we'll have a cos square theta, and here we'll have sin square theta. Cos square theta plus sin square theta will be 1. Similarly, here we'll have a sin theta, cos theta. Here it's a plus, right? We have a plus here. So we'll have sin square theta plus cos square theta 1, and you'll get back. Okay, give me a moment. All right. So it's easy to check this. All right. It's a check. So we have got differentials here. This is linear. So we can also talk about, let's talk about x square plus y square. Let's just calculate x prime square plus y prime square. This is also applicable for dx prime square plus dy prime square. So I'm just leaving that differential part. All right. So if you do this, you see that this is equal to, if you square this thing, all right, this becomes x square cos square theta plus y square sin square theta plus there's a cos term 2xy cos theta sin theta. Is that clear? Okay. Similarly, if you take y prime square, right? This is x prime square, and y prime square would be x square sin square theta, okay, plus y square cos square theta minus 2xy sin theta cos theta. Right? So if you have a little bit of idea about this trigonometric identities, just by inspection, you know that this kind of a transformation will leave this interval invariant, because it's a plus here, and we know that cos square theta plus sin square theta is 1. All right, you just look at this. This is cos square theta plus sin square theta is 1. So this is x square plus y square. All right, so these terms get cancelled. That's why we need a minus sign here. So these two terms get cancelled. All right, so we'll get also, if you do it for differentials, you'll get dx prime square plus dy prime square is equal to dx square plus dy square. Right. Okay. So this is the transformation that leaves it invariant, and I am again repeating that just by inspection we can find this. Right. It should be some cos theta and sin theta, because it's a plus here, and cos square theta plus sin square theta is equal to 1. All right. Okay. So this is one way to write the transformation. This is known as a rotation. Right. This is known as the rotation, this rotation of the coordinates. All right, this is known as a rotation of the coordinates. All right, so this means that we can write this as a matrix like this: x prime y prime is equal to cos theta sin theta minus sin theta cos theta. All right, x y. All right. Okay. We can write as a matrix, and this is known as a rotation matrix. We can call it as R. Right, or simply you can, maybe in an index notation, you can write this as this x prime you can write as x you can write as x1 and y as x2. So you can also write this in the index notation. Okay, this is usually done here. All right, you can write x as x1. We'll write an upper index. All right, y we'll call it as x2. Okay, and then this relation becomes, we see that x1 prime x2 prime is equal to, okay, cos theta sin theta minus sin theta cos theta, right? x1 x2. Am I right? Or we can simply write it like this: xi prime is equal to r I j xj. It doesn't really matter how we write this in the space part, but okay, I'm implying Einstein summation convention. Einstein summation convention. So this is just a matrix. This Rij are the components of the rotation matrix. Right. So this multiplication, you can write it also in this index form. Right. You see that J is somewhere, there's I here and there's I there. Right. This prime means that we are talking about a different coordinate system. Okay. Is this all right? Now, I'm assuming that we are familiar with these things. I'm just putting it in a different perspective. Right? I'm just putting it in a different, I'm just explaining it in a different order so that we can go to space-time by simply generalizing this discussion. Is this all right?
Board blur right and board.
Yeah, so we can write it like this. All right? These transformations, we can write it as xi prime is equal to Rij xj. This is known as a rotation matrix. Rotation matrix. Rotation matrix. All right. Okay. Now, if you look here, when you rotate, right, the new x coordinate is actually a combination of the old x and y coordinates. All right, you see that x prime is equal to x cos theta plus y sin theta. All right, and y prime is equal to minus x sin theta plus y cos theta. Okay, you see that this new x coordinate that you are talking about is a combination of the old x and y coordinates. It's a mix of old x and y coordinates. All right, so by rotating the coordinate system, we are just mixing up the terms. All right, but this does not make any physical change, as we saw the length of an object, for example, or the distance between these 2 points remains invariant under these rotations. Okay, so you can write it like this. So if we call this as a x and y axis, all right, we can choose this x and this as the x and y axis, or equivalently someone else could use this coordinate. Okay, this x and this are also perpendicular, x prime and y prime, and this angle would be theta. Okay, this is just a rotated coordinate system rotated by an angle theta with respect to this. Okay, right now see, if you are talking about this space, right, so in order to describe the physics happening in this space or anything, the geometry that's happening in this space, you can either choose x or y as the coordinates, or you could choose x prime and y prime as the coordinates, or you could choose any axis as the coordinates. All right, any x prime and any x and y as the coordinates. All right, this means that all right, I'm interpreting it like this. Right? The separation of, I'll call it like this, space, okay, into x and y is not unique, right? There is not just one way to separate the space into x and y coordinates. All right, it's not unique. You could do it in a number of different ways. You could do it in an infinite number of ways. Is this clear? So you can say that the separation of space into space and space is not unique, right? So one observer may choose this as the coordinate system, someone else may choose this as the coordinate system, but it doesn't change anything, right? So just by choosing the coordinate system, nothing changes, all right? So whatever you need to describe, either you describe this or this, the laws of physics, everything remains the same, whichever coordinate system you choose, all right? So there is no, see, this means that there is no preferred reference frame, right? There is no preferred separation of this flat space into x and y axis. Right? You could choose any two perpendicular directions as the axis. Okay, is this clear? The separation of space into x and y is not unique. Right? Or x and y directions is not unique. Right? Is this clear? So I'm just saying this explicitly, so it will be making similar kind of space, the statements in the case of space-time. Okay. Okay. So obviously, what one observer sees as x-axis, right? Right. What one observer sees as I'll also write this. What one observer calls x, right? Some other observer can call the same thing as a combination of as a combination of x and y, right? I'm just making this explicit, right? So what one observes as x, the x coordinate, some other observer will say that it's not purely x, it's a combination of x and y, all right? So one observer has separated this space into x and y axis. Another observer has separated that into x prime and y prime axis, all right? So what this primed observer, let's call him as s prime and this as s, what s prime calls as the x-axis is a combination of what s calls as x-axis and y-axis, all right? Is this clear? Okay, I hope that's clear. So you already know what we mean by this. Later on, the similar statement that we are going to make in the case of space-time is the separation of space-time into space and time is not unique. That's what we are going to say. Okay, just jumping ahead. And we'll also say that what one observer calls as x, all right, or time, because it's space-time. Okay. So what one observer calls as space, the other observer may call as a combination of space and time. Similarly, what one observer calls as time, another observer will call it as combination of space and time. Okay, that's what we are, that's the thing that we are coming into. Okay, all right. Fine.
Fine.
I'll just give you one more interesting fact about this geometry. Okay, so let's choose one particular coordinate system, x and y. We have got 2 points. Okay? You need to travel from point A to point B. You need to travel from point A to point B. Okay? You could choose a straight line like that. Right? You could choose a straight line from A to B. That would be the shortest distance. All right. Okay, but you could also take some other roundabout route. Am I right? There are any number of ways that you can reach here. Am I right? And how do you measure the distance along the path? You can measure the distance along the path. Distance along the path you take can be measured using what you call as an odometer. You know what an odometer is? Okay, you may have it in your bike or car, right? It shows what distance you have traveled. Okay, so you could go from Ernakulam to Trivandrum via Aleppi or via Alappuzha or via Kottayam. All right, these are different paths. Okay, and you know that for each path the distance you travel is different. There's nothing surprising about this. Okay, so if you travel this path, if you travel along this path, your odometer, you know that in your vehicle, there's a apparatus that shows you how many kilometers you have traveled. All right, that apparatus will show different readings. Okay, so we can say that an odometer shows different readings for different paths. There's nothing surprising about this. All right, this is no, because if you take a long roundabout way, you'll have a long you'll have traveled a longer distance. If you take a straight line path, you will have traveled a shorter distance, and this will be shown on your odometer. Okay, this apparatus is known as odometer. Is this clear? There's nothing surprising here, right? The distance you traveled depends on the path you take. Okay, you can say that. We'll just make it explicit. Distance traveled in space, let's call space, okay, depends on the path taken. All right. And there's another thing, you see that the shortest distance is the straight line path. Right? And this is actually a consequence of the geometry, right? This is because the geometry is Pythagorean, right? The shortest distance is a straight line. This is, you can say this is the consequence of geometry. Okay, of the Euclidean geometry, right? So Euclidean geometry is characterized by the fact that the shortest distance between 2 points, all right, is a straight line. You can actually prove this by making this into small sections and using the same d square equal to dx square plus dy square, finding the complete path length, etc. Okay, this can be done. Okay, so that's our discussion about space and geometry. And now let's go to a discussion of space, time, and geometry. All right. So discussion will be just a generalization of this. Okay, so let's talk about space-time geometry. Okay, what we discussed so far is the space geometry. Now we'll discuss space-time geometry. All right. Okay, now the idea is that, okay, the idea is like this. So Einstein studied this relativity, and he found that the speed, there's an invariant speed, etc. Right? He got so many effects like length contraction, time dilation, and he knew that there are transformations called Lorentz transformations, which are the correct transformation between inertial frames, etc. Right? So Minkowski realized that all these things, okay, it's saying something about space-time itself, right? It's saying that space-time has a particular geometry. It's Minkowski who actually made this geometric formulation, all right? Hermann Minkowski. He was Einstein's teacher at that time, all right? So Minkowski gave this geometric formulation, geometry of space-time. So what Minkowski said is this: all of special theory of relativity, all effects of special theory of relativity can be understood if you assume that space-time has a definite structure and a geometry. Right? So from this geometry, we can understand all of special theory of relativity. All right. Now, without knowing anything, again, just out of mathematical curiosity, just like we studied this interval, right? ds square is equal to dx square plus dy square, right? Just as we studied this geometry, we could study we could just examine different geometries. We could examine different, just assume that space-time has a geometry. This may be correct or not, but we can mathematically do it. Right? There's nothing geometries. Okay. In particular, we want to examine many other possible geometries. For example, we could just generalize the other thing. You could just generalize this thing. D square is equal to c square dt square plus dx square plus dy square plus dz square. Okay, this is just Euclidean four-dimensional space-time. This would be, if this is the geometry, then this would be Euclidean, let's say Euclidean space-time. All right. So the thing is that you have to, there's no reason why a particular geometry is there, but we have to understand what geometry is actually about, of the what the actual geometry of space-time is, right? And we'll see that this geometry does not reproduce the experimental results. All right. So this does not give the correct behavior. Right. We could examine another geometry. ds square is equal to c square dt square minus dx square. Again, I am taking only two-dimensional space-time. Okay, two-dimensional space-time, and the axis I write it as ct and x. Right, ct and x. All right. So we also have y and z. So if you have y and z, that would be dy square minus dz square. That's all. Right. We could study this particular geometry and look at the consequences. Right? Let's assume that, suppose space-time has this geometry. What do we expect? Right? What kind of behavior do we expect? All right. This means that this geometry means that, right? This is not the correct geometry. This geometry means that this gives you some sort of a measure of distance between 2 points in space-time. All right. So distance, I'll put it in inverted comma. Okay, it's a generalized distance. So we are talking about a space-time now. We are talking about a space-time. So on one axis, instead of y and x, we have ct and x. All right, so we have got ct and x. All right. So now, even in Newtonian physics, we could have written the ct and x. Nothing stops us from doing that. And we know how things travel. Right? If an object is at rest, it just moves in time. Right? If an object is at rest, it just moves in time. Am I right? Every object moves in time. Okay. So if you look at this pen here, at this moment it's here. Next moment is also it's here. Right? Next moment also it's here. So it's at this point at all these times. All right. So this is a straight line. And this line is called the world line. Okay. So we'll just clarify some of the notations. Trajectories in space-times. Trajectories in space-time are called world lines. Okay, world lines. Trajectories in space-time are called world lines. Okay, so this is the world line of a particle at rest, an object at rest. Okay, now if an object is traveling at some speed v, then you would have something like this, right? World line of particle traveling at speed v. Okay, world line of particle which travels at a speed v. Okay, so that would be just the velocity will determine the slope of this line. Am I right? The velocity will determine the slope of this line. Why do we have a c here? Okay, at this point of time, at this point, c is just a conversion factor. Right? We need a conversion factor because dx and dt have different units. Dx and dt have different units, which means that we'll need a conversion factor. In order to write it like this, we'll need a conversion factor like this. All right, and this should have the dimensions of velocity. This should have the dimensions of velocity. Okay. Now let's study the consequences of this particular geometry. Is this clear now? Is the basics of our discussion clear? We are studying this particular geometry, and since okay, if you have any question, you can ask. This is a very interesting thing. All right, so we'll have okay, we are talking about this geometry. Ds square is equal to c square dt square minus dx square. Okay, so now if you look at this, okay, it has a different property because of this minus sign here. If it was plus, it was Euclidean. We already know Euclidean geometry, but it's a minus sign here. Okay, so this minus sign makes a lot of differences. For example, this ds square can be, it could be positive, negative, or zero. All right, in this case, this ds square could be positive because there's a minus sign here. If dt, c dt is greater than dx, then this is positive. It could be zero. It could be negative, right? It could even be zero. Right? The what we call as distance, it can be negative, it can be positive, it can be zero. We'll classify these things later on. All right. If it is positive, we say that this interval, right? This interval is space-like. If it's positive, we say it's time-like. If it's negative, we say it's space-like. And if it's zero, we call it as light-like. But we'll discuss this later on. The important thing is that it can be zero. It can be zero. ds square can be zero. So let's just write for zero. Zero is equal to c square dt square minus dx square. And this combination is invariant. Okay, I didn't come to that. Let's discuss. It could also be zero. Now let's look at transformations. Just leave it at that. Let's look at, just as we looked for the transformations that leave the ds square is equal to dx square plus dy square. Okay, we checked the transformations that leaves this distance invariant or this quantity invariant. We saw that these are called rotations. Okay. Now we can also check the transformations because this is a geometry quantity. We are defining a geometry by this relation. This is a geometry quantity. So it has to be invariant under some kind of transformation. All right. So let's look at the transformations. What transformations leave ds square invariant? Okay, what transformations leave ds square invariant? Okay, again, simply by inspection. Earlier, right? Earlier we had a plus here. We had a plus here, plus of two square terms. So we involved cos theta and sin theta. All right, we involved cos theta and sin theta because we have a plus there. We know that cos square theta plus sin square theta will be equal to 1, and you will get back. All right, you will get back this relation. That's why we chose cos theta and sin theta. Here we have got a minus sign. Pardon? Can you hear me?
Clear ആവുന്നുണ്ട് പക്ഷെ ബോർഡ് വീണ്ടും ബ്ലർ ആയിട്ടുണ്ട്.
No. Okay. So we said that we talked about this thing ds square is equal to dx square plus dy square, and because it's a plus and we are adding square, we said that all right, this kind of transformation, all right, we can involve a transformation involving cos theta and sin theta. When you square and add cos square theta plus sin square theta is 1, and that kind of transformations would leave this invariant. Okay. All right. In a similar way, we look here, we've got a minus sign here, right? We've got a minus sign over there instead of a plus. So just from this experience, we know that we can give a transformation that involves hyperbolic sines and cosines, all right? For example, we can use cos h phi and sin h phi, right? And we know that cos square h phi minus sin square h phi is equal to 1. All right. So we can use, just by inspection, we can find a transformation involving hyperbolic sines and cosines. Okay, just generalizing this, because it's a minus here. It was a plus here. We use the idea that cos square theta plus sin square theta is 1. Here it's a minus, so we'll use the idea that cos h square phi minus cos h square phi, right? Cos h square phi minus sin h square phi is equal to 1. Okay, that's what we'll do. So with some experience, we know that, or just trial and error, we know that this transformation, right, Ct prime is equal to Ct cos h phi minus x sin h phi, right? And x prime is equal to minus Ct sin h phi plus x cos h phi, right? By inspection, you know that this transformation will leave this interval invariant. This can be easily checked. Right? This can be easily checked. Let's check it. So for example, let's find the quantity Ct prime square minus x prime square. Okay, so this would be, just square this thing. Ct prime square is, we'll get Ct square cos h square phi, all right, plus x square sin h square phi, and there's a minus sign. Okay, minus Ct square sin h square phi, all right, and minus x square cos h square phi. Okay, that's not all. There's the cos term also. There's also the cos term. Okay, here we'll have a minus 2 x ct, okay, cos h phi sin h phi. Just square this thing, right? A plus b whole square. So this is the 2ab term. And here we'll have, because there's a minus here, right? You are just finding c square dt square minus dx square, all right? So because of that minus, this will become a plus 2xct cos h phi sin h phi, and these two terms will get cancelled. What you have here is ct square cos h square phi minus sin h square phi. Am I right? So this is equal to, because cos h square phi minus sin square phi is 1, this becomes simply ct square, all right? And what about this? This is x square sin h square phi minus x square cos h square phi. Sin h square phi minus cos h square phi is minus 1, so we'll get a minus x square here. Right? So you see that ct prime square minus x prime square is equal to ct square minus x square if we make this particular coordinate transformation, or this particular transformation, right, of space and time. Is this clear?
Clear. Board and clear ato.
Adele. Okay, the setting mark in the class. Okay.
Clear.
Okay, good. ഈ ക്ലാസ് റീറെക്കോർഡ് ചെയ്യണോ അതോ മുൻപത്തെ തന്നെ മതിയോ? റെക്കോർഡ് ചെയ്തിട്ടാ മതി?
മതി റെക്കോർഡ് ചെയ്യണ്ട.
Okay, all right. So that's this transformation leaves it invariant. This is obvious. Okay. Now just as a note, okay, there are also other transformations that leave this invariant. Okay, ds square is equal to c square dt square minus dx square. I'm just writing all the other things, minus dy square minus dz square. Right? There are other transformation that leaves this invariant. Particularly, if you take a spatial rotation, okay, this minus you can pull outside, so this would be, okay. If you take a spatial rotation of x, y, and z, right, you know that dx square plus dy square plus dz square is invariant under rotation. So again, this will be invariant. All right. So this is invariant also under other transformations, but we are interested only in this. Right. I'll just give this. This is invariant under spatial rotations. Spatial rotations means rotation among x, y, and z only, not time involved. Okay, spatial rotations. And there are also space-time translations. Space-time translations. Space-time translation means you change t, x, y, and z by a constant, right? Each by a constant. You move it in time because it's a d here, right? It's a d here. If you add a constant to t, that d of that constant will be 0, right? So you can add constants to this t, x, y, and z. These are space-time translations. So under space-time translations also this is invariant, okay? But we are interested only in this particular transformation, okay? Okay. We are interested only in this. We are just, okay, this is important for us. We are interested in this particular transformation, all right? Okay. Now these transformations, all right, or we can write this as Ct prime x prime is equal to, so you can write as a matrix. You will have a cos h phi minus sin h phi, okay, minus sin h phi and cos h phi. X, y, right? You can write it like this, okay? Or usually it's written in this form also. You can write Ct prime is equal to x0 and x as x1, y as x2, etc. All right, we are not writing all these things. So then this can be written as x0, x1 is equal to, okay, this we can write this matrix as some lambda, okay, x0, x equal to, I'll write all the coordinates, all right, x2, x3. There are 4 coordinates, x1, x2, x3 are x, y, and z. We can write this as, okay, I think in matrix notation we usually write it as like this, all right. X mu prime is equal to lambda mu prime nu x nu, right? X mu prime is equal to lambda mu prime nu x nu, just as we wrote earlier. X I prime is equal to R I prime j x j, right? In the same way, right? You see that x mu prime, and this is known as the, this was the rotation matrix, and this is the Lorentz transformation matrix. This is known as the Lorentz transformation matrix, but we'll come to that. Okay, I think I jumped ahead a little bit. All right. Right. Now let's just, what does this looks a bit abstract, all right? This phi and all these things, it looks a bit abstract. Okay. Let's see if we can make connection with our more familiar transformations, all right? Let's look at this transformation data. So again, you see that here, the new time coordinate, all right? The new time coordinate is a combination of old time coordinate and old space, all right? So you see that the new time coordinate is a combination of old time and old space, all right? This means that if this is the geometry, this means that here already we get the results that the separation of space-time to space and time is not unique, okay? Suppose if this is the geometry, this means that what an observer calls as time, right? What one observer calls as time can be a combination of what the another observer calls as space and time, right? So the unprimed observer calls something as time and some other quantity as space, right? And the primed observer calls some combination of this space and time as his new time, right? So what one observer calls space can be a combination of space and time for another observer. What one observer calls as space can be a combination of what one observer calls as time can be a combination of space and time of another observer, right? So what one observer calls time, another observer need not agree that this is time. So this is the reason why we have all this time dilation and all that. Okay, it's not actually clock's running law. It's just because they separate space-time into space and time in different ways. All right, just like you do x, y, okay, and x prime, y prime. Okay. One observer may say this is ct x. For another observer, he'll take another coordinate system ct prime x prime, right? And this, what this observer calls as time, need not be the time of another observer, etc. Right? So you get these results from the geometry itself. Well, now let's just look at this point x prime equal to 0. Okay, look at the point specified by, given by, defined by x prime is equal to 0. Right? There is a point in space-time which is defined by x prime is equal to 0, which means that, you could write it in differential form also. Okay, let's write it in differential form. Okay, so that's for, let's say, c delta. All right, it's all right. We'll write it like this. Okay, we can also write it in differential form as we wrote for Lorentz transform. Let's look at the point defined by x prime equal to 0. So you see that you put x prime equal to 0, you see that ct sine h phi is equal to x cos h phi, all right? Or you see that you just rearrange this, x divided by ct is equal to tan h phi, right? X divided by ct is equal to tan h phi, all right? So the point x prime equal to 0, right? One point specified by x prime equal to 0. This is in the prime coordinate, x prime equal to 0. You see that it's moving at the velocity x by t, all right? It's moving, or you see that the point defined by x prime equal to 0 is moving. You see that there's an x by t here, right? With a velocity v, right? It's moving at a velocity v, as seen by unprimed observer. Okay, and that v, and this is related by, you see that v by c is equal to tan h phi. Okay, and here you see that this phi that we have here, is related to the velocity in this way. Phi is equal to tan h inverse of v by c. Right, you see that phi is equal to tan h inverse of v by c. Right, and this is known as the rapidity. This parameter is known as the rapidity. Okay, this can be asked for, I don't know, for multiple choice question. What's the rapidity, or what's the relation between rapidity and velocity? Okay, and usually we use the notation v by c equal to beta, so you can write phi is equal to tan h inverse of beta. Okay, is this clear? Okay, I'll just wind up by, so if you just substitute this back in the transformations, right? If you just substitute this back in the transformations, we had the transformations, what we called as boost. Let me write it. Just write it here, right? The transformations that we are talking about are this: ct prime is equal to ct cos h phi minus x sin h phi, okay, and x prime is equal to minus ct sin h phi plus x cos h phi. Okay, this is the transformation that we are talking about. Now we just substitute phi equal to tan n h inverse of v by c in this. Okay, so in other words, we want to write cos h phi and sin h phi in terms of, we need to write cos h phi and sin h phi in terms of v and c. Okay, that's what we want to do. Okay, so there are different ways of doing it. We can do it like this. Okay, so we can do it like this. So if we already know that, I'll use the term beta here. Right, I'll use v by c is equal to beta. Okay, I'll be using this. So you see that tan h phi, we already saw that tan h phi is equal to beta. Tan h phi is equal to beta. Okay, this means that sin h phi divided by cos h phi is equal to beta. Okay, now we need to eliminate this sin h phi and cos h phi. All right, or you need to find sin h phi in terms of beta. So you can write this as sin h square phi is equal to beta square cos h square phi. Okay, I'm just squaring. I need to eliminate the sin h square. All right, so I write this as, so I'm sorry, I need to solve for sin h phi. So I can use the identity here. So you see that sin h square phi is equal to beta square. What's cos h square phi? You can write it as 1 plus sin h square phi. Am I right? Am I right? You can write cos h square phi as 1 plus sin h square phi. Correct? All right. So you see that you can just bring the sine square phi to this side. So that will become 1 minus beta square. And you see that sine h square phi. You just solve for this. You just bring this here. Beta square will remain here. This will become sine h square phi minus beta square sine h square phi. You can pull sine h square phi outside, and that would be 1 minus beta square. So this would be beta square divided by 1 minus beta square. Right? That is sine h square phi. And similarly, so you can write sine h phi. Sine h phi is equal to beta divided by square root of 1 minus beta square. Right? And what's cos h phi? What's cos h phi? You look at cos h phi, you see that cos h phi is equal to
ആർക്കെങ്കിലും ബോർഡ് കാണുന്നുണ്ടോ?
എന്താണ്?
എനിക്ക് ബോർഡ് കാണുന്നില്ല.
എനിക്ക് കാണാം കേട്ടോ.
എനിക്കും കാണാം.
റഫീഖിന് കാണുന്നില്ലേ?
റഫീഖിന്റെ
ആർക്കാ കാണാത്ത? ജിൻസ്മോനാണോ കാണാത്തത്?
എനിക്ക് കാണാം സാറേ, ക്ലിയറാ.
ഞാൻ എന്താ വീഡിയോ ഇടാം, അത് നോക്കിയിട്ട്. ഓക്കെ, അപ്പൊ അത് കിട്ടാത്തത് നോക്കിയാൽ നമുക്ക് അടുത്ത ക്ലാസ് കറക്റ്റ് ആക്കാം. എന്തോ ഒരു പ്രശ്നം പറ്റിയിട്ടുണ്ട്. ചിലപ്പോൾ നെറ്റ്വർക്കിന്റെ ആയിരിക്കാം.
നെറ്റ്വർക്കിന്റെ ആണെന്ന് തോന്നണം സാറേ, ഇടയ്ക്ക് വളരെ ക്ലിയർ ആണ്.
ഓക്കെ,
എനിക്കൊരു പ്രശ്നം തോന്നണില്ല. ആക്ച്വലി ഭയങ്കര ക്ലിയർ ആണ്.
So shall I continue?
Yes.
Yes.
Okay, so cos h phi is equal to, you see from here, cos h phi is equal to sin h phi divided by beta. Okay, cos h phi is equal to sin h phi divided by beta. So you see that it's equal to 1 by square root of 1 minus beta square. Right? Now you just substitute all these things inside. You see that ct prime is equal to ct, okay, ct divided by square root of 1 minus beta square, okay, minus you have got x sin h phi, right? So x beta divided by square root of 1 minus beta square, and we know that the square root of 1 minus beta square, right? This is 1 by square root of 1 minus beta square. This is nothing but 1 by square root of 1 minus v square by c square, and this we call it as gamma. Okay, so you see that ct prime is equal to gamma ct minus x v by c. Okay, or t prime is equal to gamma t minus vx by c square. Am I right? All right. Similarly, you see for x prime. Similarly, you see for x prime. Okay, x prime is equal to minus ct sin h phi is beta by square root of 1 minus beta square. Okay, and cos h phi plus x cos h phi is 1 by square root of 1 minus beta square. Okay, so you see that this 1 by square root of 1 minus beta square is gamma. So x prime is equal to gamma. You have got an x there. Okay, this is beta. Okay, beta is v by c. So it's x, there's a minus sign there, x minus vt, right? I'm rewriting the ct prime or t prime is equal to gamma t minus vx by c square. Right? So these are the familiar Lorentz transformations. All right. So just by abstract calculations, we have come back to the Lorentz transformations. All right. I'll just tell you how we obtained this. We just looked at this geometry. All right. We just said, all right, let's check the consequences of this geometry. Okay, let's assume space-time has this geometry, and what are the consequences, right? And we saw that there are a class of transformations called boost. Okay, we called it as boost, which leave this invariant. And what are these transformations? These are the Lorentz transformations. All right. So just by taking this as the postulate, you can get all of special theory of relativity. We have got the Lorentz transformations from here. Okay. And we see that this quantity is invariant under these transformations, and we called this phi as rapidity. Right? So you can write the Lorentz transformations. These are known as Lorentz boosts. Lorentz boost in terms of the rapidity or in terms of the velocity. Okay, rapidity has some physical meaning, but we won't be going too deep into that. Okay? It's just to understand the geometry. So we just looked at this geometry, right, and then we obtained it. Now let's look at this thing that we said that this ds square can be equal to 0. You see that ds square can be equal to 0. This is a possible thing. Okay. So if ds square is 0, this means that 0 is equal to, in the case, because it's a minus sign here, all right? There's a minus sign here. Okay, so it can be 0. So if you just look at this possibility, 0 is equal to c square dt square minus dx square, or this means that c square dt square is equal to dx square, or c square is equal to dx square or dx by dt square. All right. Now, what does this mean? Or c is equal to dx by dt. Okay, this means that we said that this is invariant. All right, this combination is invariant. This is Lorentz invariant. Okay, if this is Lorentz invariant, this is Lorentz invariant, this is also invariant, this is also invariant. And what's this? This is the speed. Okay, c is equal to dx by dt. This is an invariant quantity. All right. So this means that if you assume this geometry, all right, if you assume this geometry, there has to be an invariant speed. There has to be a Lorentz invariant speed, a fundamental speed, which is Lorentz invariant. All right. Now this light happens to travel at this speed. All right. Light happens to travel at this speed. But if you notice, we haven't said anything about light so far. All right. We just said let's look at this geometry. All right. So this light thing is not important. Light is not very fundamental to special theory of relativity. Even if light was not traveling at this particular speed, you can just study the consequence of this geometry. All right. This could be some other speed. This could be some other speed. But now we know that light happens to travel at this speed. Okay. So light is not really fundamental to special theory of relativity. Even though when we study relativity, we always talk about this light and all that. It's not really fundamental. Okay, you can formulate special theory of relativity without talking about light at all. Okay, so we can just study the consequences of this geometry, and we'll see that if this is the geometry of spacetime, there has to be an invariant speed. Okay, now from experience and from other theories, we know that light happens to travel at this speed in vacuum, only in vacuum. All right, only in vacuum. So we don't need this light. You don't need any assumption about light in order to derive special theory of relativity. You can understand it as a consequence of this particular geometry. All right. Okay. There are other possibilities that this can be minus and plus and 0. We'll talk about these things in the next class. If you have any doubts about this, you can ask now. All right. So it doesn't matter whether light travels at a different speed in a medium or not. It does not change special theory of relativity. Even if light traveled at some other speed, it would not affect special theory of relativity. Special theory of relativity would still be true if this is the geometry of spacetime. All right. So all of special theory of relativity comes because spacetime has a geometry, an underlying geometry. And what Einstein did was that Einstein recognized that spacetime has a geometry through some other physical things. All right. So all this can be explained by this geometry. This geometry is known as Minkowski geometry. Minkowski geometry. All right. The other one was Euclidean, and this is Minkowski geometry. All right. One more thing. And here you see that earlier in Euclidean, we had an odometer, right? We had an odometer. What did odometer do? It measured the distance traveled along different paths in space, right? In the place of odometer, the generalization in Minkowski spacetime, what we have is a clock. Okay, what we have is a clock. Right? So this means that if you take, we'll discuss this a little bit more. CTX, if you take a clock to different paths on spacetime. Okay, if you take a clock to different paths in spacetime. Okay. This is A and B, right? You can take a clock to different paths in spacetime, and each of this clock will show you a different reading. Obviously, why? Because each of this clock travels a different distance in spacetime, right? So in terms, so this is again, if you look at it like this, there's nothing surprising that different clocks show different readings, because what clocks measure is actually a distance in spacetime. Okay, clocks measure a sort of distance in spacetime. Okay, so clocks are just like odometers. So what we see here is that clocks are just like odometer. Okay, it measures the distance along space. And this is why we have all this twin paradox, all right? There are a pair of twins, one of them travels at a high speed and comes back. Okay, another twin stays on Earth. Right? So if you are familiar with the twin paradox, but we'll elaborate this a little bit before the next problem session, all right? So you've got a pair of twins, A and A, right? And one of the twins remains at home after their 20th birthday or something, and his world line is like that, okay? And another twin goes at a high speed travel and returns, right? And when they come back, their ages will be different. Their age will be different, all right? This is the famous or notorious twin paradox. So obviously, according to this formulation, the clock traveled along this path shows a different time than the clock traveled along this path. That's because of the underlying geometry, all right? And clocks show the distance traveled in space-time, or distance along certain paths. Right? But we'll elaborate a little bit on that in the next class. If you have any questions, you can ask now. Is this okay?
Okay.